Elementary operations or elementary transformations of a matrix. Objectives: to understand and perform elementary row and column operations through illustrations. Any elementary transformation is called a row transformation when applied to rows, or column transformation when applied to columns. 6 types of elementary operations or transformations can be performed on a matrix, 3 of them on rows called row operations, and 3 others on columns known as column operations. Let us discuss them one by one. Let us first understand elementary operation of type 1, that is, the interchange of any 2 rows or columns. The elementary operations of interchange of the ith row with the jth row is denoted by Ri, interchange Rj, and interchange of ith column with jth column is denoted by Ci, interchange Cj. For example, if A is equal to matrix, by applying the operation R1 interchange R3 to interchange the first row with the third row, matrix A transforms to matrix B equal to matrix. Elementary operation of type 2 involves multiplication of elements of any row or column with a non-zero number. Here, the elementary operation of multiplication of elements of the ith row by a non-zero number k, denoted by Ri, is replaced with Kri. Similarly, multiplication of elements of the ith column by a non-zero number k, denoted by Ci, is replaced with Kci. For example, if A is equal to matrix, on multiplying elements of the third column of matrix A by 2, that is, on applying C3 is replaced with 2C3, we get the new matrix B equal to. Elementary operations of type 3 involves addition of elements of any row or column and the corresponding elements of any other row or column multiplied by a non-zero number. The elementary operation of addition of elements of the ith row to the corresponding elements of the jth row multiplied by a non-zero number k, denoted by the expression Ri, is replaced with Ri plus Krj. Similarly, the elementary operation of addition of elements of the ith column to the corresponding elements of the jth column multiplied by a non-zero number k, denoted by the expression Ci, is replaced with Ci plus Kcj. For example, if A is equal to matrix and B is equal to matrix, on applying the elementary operation C2 replaced with C2 plus 2C1, matrix A is transformed to matrix B. Equivalent matrices. 2 matrices A and B are said to be equivalent if one can be obtained from the other by applying a finite number of elementary operations on the other matrix. If A and B are equivalent matrices, symbolically, the relation between the two can be written A equivalent to B. Let A be equal to matrix and B be equal to matrix. Now A equal to matrix. On applying the elementary operation R1 is interchanged with R2, and we get a matrix that is equivalent to matrix B, that is 2, 3, 8, 1, 2, 6, 2, 0, 10. By applying the elementary operation, C3 is replaced with 2C3. Let A, B and X be three matrices of the same order such that X is equal to AB. On applying a sequence of row operations on the matrix equation, X is equal to AB, these rows operations being applied on X and on the first matrix A of product AB simultaneously, the matrix equation is still valid. Similarly, a sequence of elementary column operations on the matrix equation X is equal to AB can be applied simultaneously on X and on the second matrix B of the product AB, and the equation will be still valid inverse of a matrix by elementary row operations. Using the row operation, let us apply a series of row operations on A is equal to IA till we get I is equal to BA. Now, by definition of inverse of a matrix, B is equal to A inverse. Using column operation, a series of column operations is applied on A is equal to AI till we get I is equal to AB. By definition, inverse of B is inverse of A. Illustration. Obtain the inverse of a matrix A is equal to using elementary operations. Using the row operation, A is equal to IA. Matrix is equal to matrix into A. By applying the operation, R1 is interchanged with R2. We get matrix into A. By applying the operation, R3 is replaced with R3 minus 3R1, we get matrix is equal to matrix. By applying the operation, R1 is replaced with R1 minus 2R2. We get matrix is equal to matrix. By applying the operation, R3 is replaced with R3 plus 5R2. We get matrix. By applying the operation, R3 is replaced with R3 divided by 2. We get matrix into A. By applying the operation, R1 is replaced with R1 plus R3. By applying the operation, R2 is replaced with R2 minus 2R3. We get matrix into A. Hence, A inverse is equal to matrix 1 by 2, minus 1 by 2, 1 by 2, minus 4, 3 minus 1, 5 by 2 minus 3 by 2, 1 by 2. Summary.